This is silver, though it doesn't.
Are galaxies moving faster than the speed of light? According to Albert Einstein, nothing moves faster than the speed of light, but that's only true for objects moving through space. Our universe is expanding. It stretches just
Unless it's in water, then light can't move faster than some of the fastest stuff that there is.
like dough in an oven. All the galaxies inside this cosmic dough recede from each other as it expands.
No. Stuff just floats and moves away. Although, I mean, okay. Here's the thing. I've been recently talking about the EM field being everywhere. And that being said, considering that every source of mass is considered to be also an influencer, emit like any star, it's just emitting tons of light that, like any solar cell, should be pushing everything else. And I'm not saying it's light doing this, but the EM field is also flowing outward in all directions. It is possible that there is an effect from every planet, every solar system, every galaxy towards each other, an outward pressure that is literally, besides their normal drift through space, is pushing all parts away from other nearby parts. And as much as that might be the case, again, there's something you have to realize about this. It's happening at a very predicted, constant rate. And as long as you're able to move your ship faster than the stretching, than the supposed fabric of space-time, which is, again, it's not so much the fabric of space-time. I'm still 100% going to explain to you it is the EM field, which is what is essentially the dark matter, the fabric of space-time, the stuff that is doing the movement. It's fluid. So anything that's giving an outward pressure, like, stars sending out lots of light, all of that light is also affecting the nearby EM field, dragging it away from the source of light. So literally, every galaxy that is everything that is out there emitting light, which is pretty much everything, with very few exceptions, are pushing everything away from everything else. And this is better understood. Instead of the fabric of the universe, I'm more likely to agree and admit to the idea of it being some microfiber material compared to electrons, compared to quarks, compared to photons, even smaller. We have the EM field itself. And it's not that it's a springy thing. It's just another fluid, and like anything else, it's all moving in regards to literally all the other emitters with their pressures. So yes, the universe is all spreading out at a very consistent, regular rate. So
the farther apart they are, the faster they recede. And eventually,
that's not how this works. It is moving away at a regular rate. It is not faster. It's the fact that when you go along a xylophone, that's the wrong word. need to get the face cam on for this. When you go along a squeeze box or whatever, and it spreads out, each individual fingers are going to spread out at the same, like all of them are spreading out at the same rate. But as you can tell, in between each finger, it's only this much. That's analogous to you and your nearby star. But then you have the farther fingers, which are spreading out a vast distance more, a multiple more amount of space, right? You start here, you're really close. Here you barely move much, but here you're moving like, you get it. It's a multiple, it's a larger amount of the rate. And this is what's happening throughout all of space. Imagine that spread, but it's everywhere. And any time that you move forward, that spread rate is repeating. And those rates add up. So what happens, obviously, if you can go faster than the two smallest points are able to spread away from each other, right? Then you're able to go and you can reach the distant points, no worries, because again, it's not going faster than the speed of light. This is a hoax. This is bad science. Again, they're not thinking about how it works. Essentially, like the entire thing in the squeeze box and everything else, it's all being moved away at a rate that can be considered, compared to us, it's like it's moving faster than the speed of light, perhaps. But it's not actually. That's the thing. It's a perspective thing. So if you were to be halfway there, it would be moving half as fast away from there because the rate is happening. And as you can tell, like if you're going from the middle to the outside, right, then you have only two lengths of expanded space that you have to travel through. And if you're going from the bottom to the top, you have four lengths of expanded space, so you have even more space that is between you that is spread out. Nothing's moving faster than light out in space. It's not doing that, but anyway.
Galaxies that are far enough away recede from us faster than the speed of light.
No.
This is true for about 95% of the galaxies in the universe, but...
like, the thing is, again, it's still the same basic rate, and the fact of the multiple of the distance away is what makes it have the illusion of it being basically the speed of light, is what it looks like. But again, if you remove yourself from this local center of the dot and you move to the edge of the dot, consider that rate around here, and then suddenly that rate, the entire expansion, is centered around you at this point. And so the distances that it's expanding are different here than it is from down here, and it's way more expanding here because you've moved upward. And the further you move up, the more that expands, the more this contracts. So there's less space between wherever you're going that has because of space expansion over time. Again, this is a certain amount of distance per megaparsec. And a megaparsec is a big number, reference to a very large space. And then it's a certain amount of, like, I can look up the thing. So after 2 seconds of Googling, the expansion of the universe, the very expansion of the universe, is the inflation of the universe is suddenly expand the factor of at least 10 to the 26 in every direction, about 10 to the minus 32 of a second. I don't know what the hell they're talking about. Oh, that's nice. I like that. That's neat. It is, however, something that I can actually work with. Okay. It's expanding at a rate of 73 kilometers per second per megaparsec. A megaparsec is just a large section of space. Or it's about, the speed is about either 73 or it's about 67. This thing about, you have to understand, the thing about the microwave background is that is information that came from the very farthest distances of space, and so it may have, over the course of few billion years, been able, like tens of billions of years, been able to expand to 73 kilometers per second. Again, it's weird to think of 73 kilometers per second in relation to a megaparsec. And it's that relationship, the amount of actual space per segment that it's expanding. So it's the idea that there should be, instead of all of this, they should have a proper, the truth is you should have this as a proper ratio of expansion, but kilometers per second versus the large area is like saying, okay, every second this region gets, like in general, the areas get more spread out. And yeah, if you multiply that for 2 megaparsecs, then you'll end up with twice the amount, or 146 kilometers per second per megaparsec. And as you go to 10, then you have 730 kilometers per second. But per megaparsec. That's the thing. It's this whole large area. So what's a megaparsec? Ah, and here it is. 3.26 million light years. Now here's the thing, right? So you can't say, the thing about this is, the rule is you cannot say this, for example, about any arbitrary distance. It's not, it's moving at 73 kilometers per second, like for every light year, because that kind of expansion rate is a few million times more than what we currently estimate it as. Like 3 million times more. So, because, so if you understand it right, then an entire large 3 million light years is expanding at the rate of, for all of that distance, it's going an extra little bit per second. And that's in all directions in all of outer space. And here's the thing, yes, that can add up, and you can magically say that because of the further and further distances, that those numbers could add up and end up forming what is essentially light speed, or 100 times light speed if you go even further away. How far would you have to go really to make that happen? I don't care. The point is that, I mean, if it's millions of light years, right? And we have 13 billion or 45 billion light years, then it's like 20,000 megaparsecs. So 20,000 multiples of the speed of expansion. So we can do that math real quick. Buttons fail me. Times 73. It's a sizable chunk. Now compare that. Okay, 73 kilometers per second. So it's like 1,000,000 kilometers per second. And again, the weirdest thing is, and as much as I might not want to be a persistent of relativity, because relativity is still relativity is weird. Okay, no, relativity is still for the most part a hoax, but the way that it works with this is ironically relativity in a weird way, because again, if you move if you track the motions of it, the problem with relativity in the regards to the simultaneous lightning strikes versus a train, and the train can't coincide that it happens simultaneously. They think that the one in front happened first because they're not compensating for their own speed. That's stupid science, and that's relativity in the bad way. This is also stupid science in the bad way, in the fact that they're saying that an object moving through space with another nearby object also moving through space, all of them are moving at the 73 kilometers per hour basic, or per second. Forgive me for saying per hour. It's not relevant. It's relative. The point is that when you have this speed, you gotta realize that most things are moving away at this rate. Regardless, for some reason, even their own initial inertia, like it's electromagnetic negative pressure. And that's the real key of it, is that it is electromagnetic negative pressure. It might not be electrons, it's not electrons themselves that need to be pushed. Everything is connected to the EM field. All protons are connected to the EM field. So every piece of mass is connected to the EM field that is everywhere. So when you have a bunch of energy pushing around enough, Yeah, my galaxy can say fuck off. I'm pushing you away. But if you have your own inertia, you're gonna merge with the other nearby galaxy that's gonna come over to us and wreck our house for in a couple. Don't ask me to be accurate about this shit. It's either millions or billions of years. I don't care. It's gonna happen eventually, not near to us. So who cares? But later in the future, those two things are moving a velocity that brings them together right now. Their natural inertia is bypassing all of this stupidity, thinking that the expansion of the universe applies to literally everything, everywhere. Own inertia can easily overcome that. So that's why we are having galaxy mergers. Because, you can move with your own velocities. However fast the Milky Way is moving and the other one, and that they're going to merge together. I don't actually remember the names of them, but they're going to merge, and it's a known fact. So, yeah, it's not all just spreading out. But in regards to literally everything else that's far enough away and doesn't have its own inertia, and because things have been moving for billions of years, the general tense is that they would just spread out. There's no reason for them to not. So when you end up with something like this, gotta remember, grain of salt with this stuff.
5% of the galaxies in the universe, but we can still observe the light they emitted in the past. When the light of a distant galaxy reaches us, it's traveled through the expanding universe for a long time. So the light...
Now, here's the other part of expansion of the universe and the way that it works with the light, which is part of the EM field. They're not doing the math on this, but they're doing the math on it to say that it's going to redshift because of a certain distance that it has traveled in order to get to us. Makes it redshift. Not at all to say that it's gone through some... I mean, it's more likely that it's done that than it's gone through some atmosphere and shifted red, like in any prism. Or that signals like this will naturally shift red over a given period of time, because for the course of, like, I don't know, an extreme distance, light will just naturally redshift. The fact that there's a bunch of stuff in all directions means that light is going to continue to redshift as it passes by us and goes on its merry way. So, the problem is, in my brain, that redshifting didn't make sense with just the idea of the fabric of the universe is expanding. When I translated it into the EM field is being sent out in all directions and forcing everything else away, it makes a lot more sense, because fabric of the universe is unknowable and immaterial and doesn't have any solid evidence and whatever else, but the EM field in my brain makes 100% of sense and solidifies all of the stuff that's happening because I can quantify it and everything. And although they say it's not that, it is that.
Light itself stretches as well. By analysing how much the light has stretched, we also know how far away the galaxy is. The more
it's not at all possible that some galaxies, the parts that we're looking into, are like again, manipulated by some other atmosphere, which makes them be redshifted. It's more likely that stuff that we are looking at, because you gotta realize all the distant spaces, the telemetry of space is like this, where you don't have any clue where my fingers are in reference to the camera easily, but they're all at different distances. They're not equally distant, like this. They're like this, where one finger is the closest, then you got other fingers that are further away, and the thumb, which is the most farther away. And it's stuff like that. But then with the red shifting, like, it's a dynamic of light that if you go further and further, it will just do that. So calculating it that it is distance and the idea of expansion means you should understand it is an EM field thing happening. But that's not what they want to say. They want to say fabric of the universe. You might as well be correct. The math is okay, everything else is fine, but you're missing the nuance, and that's what's bothering me. Because what if you could stop the EM field from reaching places? Right? Is it possible to, for example, make a kind of electromagnetic ball around Earth? And would that lead to the Earth flinging out into space? Because it's no longer affected by the magnetic force that is from, that, as I am assuming, is the reason why we're connected to the sun in the first place. Or would it at least, would it weaken the connection to the sun, like, at all? That's an interesting theory. It's an interesting idea. And unfortunately, my idea is that, yeah, you do that. This is also why making a Dyson sphere is a terrible idea, because that would completely cut off the EM field. If you make a Dyson swarm, you are weakening the EM field, which still means that you have less force everywhere. But if it's a thin enough swarm, you're not weakening it enough that you actually are influencing the orbits of anything. But don't make a Dyson sphere. If you're going to make a Dyson sphere, you have to destroy the... You basically have to say you're going to abandon all other objects in the solar system, or incorporate all of them into the Dyson sphere. Otherwise, you're going to lose... I'm pretty sure you're going to, like, magnetron trap it all. Because here's what happens. I've seen it. Okay? Someone made a magnet ball. And it was designed with all of the North Poles and all the South Poles, be that they all faced the inside of the ball in the same direction. So when they put the final piece in, there was no magnetic flux that was able to go out. So it had no magnetic properties whatsoever. It was just a solid ball. Even though you know that it's magnetic, even though every piece of it is supposed to be a complete magnet, the magnetic flux wasn't able to go in and wasn't able to go out. So there is no more flow. So you literally cut off the entire flux of everything, meaning that it doesn't have any magnetism whatsoever. I think, genuinely, if you made a Dyson sphere, you would cut off the magnetic flux, and you would doom the entire rest of the solar system to just fling out into space. Because there's nothing else holding them there. Because the moment that you stop looking at space as being bent, because that's not what's happening. Space-time does not curve. Get over that. Again, it's not the magnetism of like classical magnetism. It's not the magnetism of conventional electromagnetism. It's the magnetism that happens when you have an energy flow and it's enough that it can affect even like not regularly magnetic stuff like plastic or an apple. Like everything has everything has its own magnetic moment. It is not without some ability to be influenced by the EM field. That's the whole point of what I'm trying to explain. So, literally, again, you make a Dyson sphere, there's a chance, if you make it out of, like, stuff that blocks all the magnetism, everything else is being flung out into space. It's not going to stick around anymore. That is a solid belief. I mean, you gotta realize why stuff is able to be held by a galaxy. If you were to make a Dyson sphere around the core of a galaxy, the entire galaxy would fall apart. Maybe, but not really, because you'd also have to cover. The problem is the galaxy isn't held together by just the galaxy core. It's also held together, the black hole in the center. It's not just held by that, it's held by all the other mass that's in and around all the galaxies. So if you were to cover every star in the Dyson sphere in the galaxy, then you might have it completely scatter. More likely. I don't know. It's it's more dynamic problem than I'm letting on, but it is um it is definitely something you don't want to just do, like you don't want to cover it completely. But no one's going to admit that. No one's going to agree with that because their ideas of conventional electromagnetism and those measurements are about how the electromagnetism works with regard to a connection of a proton with an electron. And they're forgetting that the EM field is everywhere, and all flow EM field, like literally if you have electrons or not, you're going to be flowing EM field. Because protons also flow EM field. So everything's going to be drifting along according to how the EM field is influenced by the mass. And obviously, the larger the mass, the more the field is affected. Like, it's why you don't have solar storms on the planet, but you have them on the sun. Because it's so many times bigger than, as there's so much more mass in a star versus a planet. It makes you wonder why there isn't coronal mass ejection stuff happening with Jupiter, but I think Jupiter is having, like, it's not nearly as much friction and hot, and it can't make those kinds of violent energy things to make a solar storm. Like, I don't think it can do it.
Stretched, the farther away it is.
So,
Are galaxies moving faster than the speed of light?
so again, no, they aren't. They're moving at their own independent rate, or in general, they're moving at the cosmic, like,
According to Albert Einstein, nothing moves faster than the speed of light.
meh. So, they're all moving at a standard rate. The rate is multiplied per distance. So, like, you have to add another rate per distance. So, again, if you have 100 amount of that distance, or 1,000, then you end up with 7,300 kilometers per second. Light is only 300 million meters per second-ish. So 300,000 kilometers per second-ish. The point is that once you get past that point, yeah, it seems like everything's moving faster than the speed of light from the distance that is. The moment you shorten that distance, you have less multiples of that, and you end up with just the rate of expansion of the nearby stuff, 1 megaparsec, which is still, it's a large area in order to go through. So millions of light years is massive. So it's like, and again, gravity overcomes the expansion of the rate of the universe stuff happening, as well as an individual inertia. So yeah, nothing's moving faster than the speed of light out there. It's just like with the rate of the spread, it is going to end up that distance over time, which makes it look like it's going faster than the speed of light, but it really isn't. It's weird. So, again, it was an interesting thing to think about. You take that rate and you go, instead of per megaparsec, you go per light year, and you have 3 million times as many intervals of the expansion of the rate of the universe. That's a massive, beyond massive, larger number for the total speed that you've achieved in the same distance, right? It'd be more like 21 billion or whatever. Don't call me on that. I'm sleepy. It doesn't matter. The point is that, yeah, if you have a ship that is capable of going faster than just even the here's the question: how fast do you actually have to go to be moving faster than that much extra distance per megaparsec? And again, it brings me back down to the rate of expansion should be a ratio of the distance and of expansion and the distance that you have to be witnessing in order to notice the expansion happening. So like for the megaparsec, which is like it's a weird, the math is crazy with this because again, kilometers and millions of light years, if one light year is 300 million meters per second or 300,000 kilometers per second, right? We can get, I want to get into, if a single light year is 300, okay, it's 298 kilometers per second. And then you have 326 of that. Let's go back to the math. So you have 398, no, sorry. What the fuck? 298, shut the fuck up. 298, a phone number. No. Times the megaparsec number, which is 326. Okay, so 971 and a half million kilometers? Right? Right. You end up wondering at what point, why is it that it is this certain distance, then we see 73 kilometers per second is what expands. Because again, if you have the shorter distance and you have the same rate of expansion, then you would have double the total rate of expansion for that initial distance. So the megaparsec, if you did like, instead it was that for half a megaparsec, then it would be 146 per megaparsec. So they figured out this math. It's a weird thing of a distance over a distance, which is the definition of acceleration. So then what is the ratio of this, is it divided by this? 13? That doesn't track. How does that track? Oh, if you cancel out the 48 or dot 48, and again, thinking about this in millions, it's still 13 million, 13.3 million of the distance per second. Does that make any sense? Does anyone talk about it as the ratio of the distance? Like, it is that is the actual thing, that if you have whatever distance that you have, you're adding every second, you're adding another 13.3 millionth of the distance that you're measuring per second. You shrink that down to the size of electrons and stuff, and we're talking about 10 to the 10th, and 10 to the 10th is 10 and 10 zeros, or it's 10 to the 11th, 11 zeros. So how big of, how, 3 is 1,000 million billion, 100 billion? Yeah, you start to realize that it's like the electromagnetic field strength. And they're not keeping up with that logic. That if you broke it down to the area, comparing in the reason I converted it into kilometers, and then I compared that to, which is a very vague, basic thing, but like the speed of light in kilometers over the distance of kilometers per second equals the ratio of distance per adding every distance per time. So it's 13.3 million. So like, if you translate that into a meter, it's 13. Again, this is in kilometers. Shut up. So I translated the megaparsec into, I assume it's like 971.5 million kilometers, or 971.5 billion meters per second. So for that vast distance, every second you're adding another. Well, that doesn't make any sense. Well, there's a huge difference between 13 billionths of the measurement and 13 millionths of a measurement, because literally one is 1,000 times bigger than the other. That's how easy things can get, like this can get messed up by forgetting that you're working in kilometers. Because this number is based off of this number, and that number is based off of light years, and light years based off of that many. Oh, but then the 298 is based off of meters per second. That's how it also can get confusing. Because it's 298 million meters per second, or 298,000 kilometers per second. And then to translate, or 298,000 kilometers times the 3.26 million. Should I be working with? The problem is I'm reducing. The problem with reducing is you can lose the decimal place and whatever. So return that back to here, we end up with so the real number we're looking at here $320 298 million, or 298,000 kilometers times the 3.26 million. This is why you need real numbers, because like if you did this with, and then you did this to the tune of, instead of this, it's actually wait, what? What is it? Okay, the problem with working with more zeros in the 3 is that you can't just do that. You have to remove that, and then that is it times 100,000, and then million. Okay, this many that's in meters per second. Translate that back to kilometers per second. That's fine. That's fine. And then it's that many of those is the parsec. Parsecs are silly. Parsec is the yard of freaking stellar distances. Parsec is literally the yard versus the meter when it comes to stellar distances. Okay. As long as we can agree what the hell it is, fine. Okay. For a factor of a few million is just an order of magnitude difference with, like, the more precise we are about how far we look into the speed of or distance of light in a year. So that, the total number of all that jizz, divided by 73, and you end up with, as I said, 13.3 billion. I was right, it is 13.3 billion. My brain was like trying to keep up with it all, and it's not, it's like, yeah, kind of, okay. So that's the ratio. It's like for every distance, you add 13.3 billion. You have to put 13.3 billion of those distances. The term is 1 out of 13.3 billion of the distance that you're measuring. You realize how close that is? Again, 10 to the 10. How big is 10 to the 11th then again? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Huh. You know, it's 10 to the 10th that you end up with the electromagnetic field area in regards to atomic matter. So expansion of the rate of the universe, and it's literally adding. So if you were to relate this to a single meter, you would have to add 1 out of 13 billionth of that, and that's the radius of an electron. Or something like that. Coincidence? I don't think so. I think that the EM field is a perfect candidate for the expansion rate of the universe, and the reason for that. And I love the idea of thinking of a ratio of 1 over 13.3 billion. Then think of whatever the hell numbers that they shoved into our face. Megaparsec. Here's what happens when you plug in the old numbers. What was it? 60? The old numbers I think used to be 63, 62, 67. So here's what happens when you plug in the old number of 67.4 kilometers per megaparsec. Remember, the 63 is in kilometers per megaparsec. This is literally just a big number saying convert the megaparsec into kilometers, and then divide that by the number of kilometers per second. Right? So we end up with 67.4. Wow. It's not that much different. Look at that. It's 14.4 versus 13.3. Sorry, what? Ah, see? Yeah. 3. 13.3. 14.4 billion ratio versus a 13.3 billion ratio. The difference is extremely tiny. If you really look at those numbers, like comparatively, the old ratio and the new ratio. That's neat. Sorry. Why do I keep putting 74? That doesn't track. Yes, all the zeros are necessary. Every zero is necessary. Even you. Anyway,